Welcome, welcome back, students. In our last lecture, we have talked about resolution, especially on spatial resolution. Now, we will talk about spectral resolution. I hope you have enjoyed the previous lecture on spatial resolution. And if you have any query, you can uh, ask me in the forum or you can ask me in our group. Now, we know we have talked in the previous lecture, in the previous topic, we have talked about spatial resolution and what is resolution and how spatial resolution keeps uh, the higher the spatial resolution, the finer the spatial resolution, the more detail can be covered. Now, in today's topic, we will talk about spectral resolution. So, what does a spectral resolution represent, and how it is different from spatial resolution, and how it is important in the remote sensing system, satellite system? We will understand today. So, spectral resolution represents the spectral bandwidth of the filter and the sensitiveness of the detector. Once again, I am repeating that it represents the spectral bandwidth of the filter and the sensitiveness of the detector. The spectral resolution may be defined as the ability of the sensor to define fine wavelength intervals. It could also be said that it is the ability of the sensor to resolve the energy received in a spectral bandwidth to characterize different constituents of Earth's surface. The finer the spectral resolution, the narrower the wavelength range for the particular channel or band. See, many times you have listened about multispectral system or hyperspectral system. So it actually shows the resolution, the spectral resolution, and the sensitiveness of this detector. The manual remote sensing, as I was explained, are multispectral. Multispectral means they record energy over separate wavelength ranges at various spectral resolution. For example, IRS list 3 uses 4 bands. That is, the band the IRS list 3 uses: green band, red band, near infrared band, and mid infrared. The bandwidth range is for around 0.52 to 0.59 for green band, 0.62 to 0.68 for red band, 0.77 to 0.86 in nanometer of course for near infrared band, and 1.55 to 1.70 in mid infrared band. Another example is the Aqua and Terra modis sensor instruments of which is a modest sensor which has been on board on Aqua and Terra satellite, uses 36 spectral band. This 36 spectral band has three visible bands. Three bands. Visible bands, but it includes three bands in visible spectrum. Recently developed hyperspectral sensors which detects hundreds of very narrow spectral band are also available. Hyperspectral images contain more information compared to multispectral band, but on the similarly, they have much to be represented. They have much to be represented, but they have a limited spatial resolution. Now, you can see, for example, there is a figure which I am showing you. So this is the hypothetical representation of remote sensing system of a system with different spectral resolution. Now, the first representation shows the DN value obtained over 9 pixel. Okay. Now, for suppose this is the first example which I am showing you. The first representation DN value obtained over 9 pixel using imaginary captured in a single band. Okay. For example, you are using a single band camera. So it will from 0.4 to 0.7 it will capture only one value. The capture image will be like this. Okay. Similarly, I have represented it the second and third, means um, in the second and third representation, the DN values obtained are in 3 and 6 band using respective sensor. If the area image is a kilometer per square, a kilometer square, the same area has been viewed using 1, 3, and 6 number of bands. Okay, the same image has been viewed here in 3 different bands. Same image has been viewed here in 6 different bands. But here, what the difference is, the band has been divided in 3 different. A single band has been divided into 3 bands. Band 1, 2, and 3. Here, the same band, one band has been divided into 6 different bands. So the the amount of information covered in this particular image is much more detailed and higher quality compared to this particular image, the first one. So that is what I want to say, that the area is imaged. For example, the area covered by this region is 8 kilometer square. Just for example, we say one whole pixel says 1, so it is 9 kilometers square. The same area has been viewed by both this, but the amount of information collected by this 3 bands and this 6 bands is much more than particular single band. Generally, the surface feature can be distinguished using multiple narrow bands. Okay, now multiple narrow bands than from a single wide band. What I want to explain with amount from this particular image, that if you use one particular band, you will get just a single band information. But if you use 6 band, that is multispectral band, you will get information about 6 features. So if there are multiple features over a same area, using different higher resolution spectral resolution uh, system, you can get more features, you can extract more features. Now the hyperspectral image, which is a very high divided narrow banded spectral resolution image sensor used in those sensor, it could be divided into the same feature. This particular band can be divided into 100 parts. So you can imagine the how much 100 parts, 1000 parts equally valued, 2000 parts equal value, then it will be a hyperspectral resolution. Now, for example, here I have shown you a particular representation to explain what this particular spectral resolution information can mean to you. Now here we are using the broad wavelength band 1. The features of A and B cannot be differentiated. Okay? For example, if I am using band 1, only one band image, you can clearly see that I can't differentiate the features based on this type of line. This minor variation can be anything, can be a minor error from the camera also. Okay. However, the spectral reflectance value of the two features are different in the narrow bands, that is other two bands, like band 2 and band 3. Okay, the band 1 is from 0.4 to 0.6. Now I divided this band into two different bands, band 2 and band 3. Band 2 is from 0.4 to 0.5, band 3 is from 0.5 to 0.6. Now if I analyze this image, my feature will be in this particular format for band 2, for band 3, and similarly for image B, it is in this particular way. The signature of the image has this difference. Thus, a multiple spectral image involving bands 2 and 3 can be used to differentiate the feature of A and B. See, we can't generate a major difference between when it is single banded, when we only see the band 1. Just imagine that you are only viewing band 1 and not band 2 and 3. But when you view band 2 and band 3 output along with band 1, you can clearly see the difference. In remote sensing, different features are identified from the image by comparing their responses over different distinct spectral bands. Broad classes such as water and vegetation can be easily separated using very broad wavelength range like visible range or infrared range. However, if you want to go in more specific class, for example vegetation type classification or rock classification or sand type classification, okay, and much fine, and for that we required much finer wavelength range, and hence a finer spectral resolution is required. For example, to show the difference, okay, you can see here a spectral resolution at different bands. Here the figure shows the different spectral resolution responses of an area for Landsat image. So Landsat has 7 bands in it. It ranges from visible band to mid-infrared band. The visible band covers blue, green and red band. It also covers near infrared band and thermal infrared band. And there are 2 bands for mid-infrared. Now you can clearly see the images. This is the total image, a total sum of all these images. Just reviewing purpose, you can clearly see how the different information has been stored in it. Now the blue band has image in this particular format, but while the green band had is this particular format. You can see the difference in each band. So it has 7 bands of a same particular area, okay, and you can see that each and every response of each and every band is different. This type of features can be used to identify particular species, okay. This is the original real-time image, color image. Now if you want to know what is the image, so you can clearly see that in this particular image here, this is the coarse resolution pan-chromatic image. A minimum information is visible from the image, very minimum information, okay? You can't understand, but when I show you a different image with different spectral bands combined together, you can help, this combination can help you to extract different information. Let's check. Now this is the particular image in coarser resolution, panchromatic image, normal image, black and white form. Nothing is been clear from it, and minimum information is visible from the image. Now this particular image, now the same area, okay. Now this particular image is formed by 3 bands, that is band 3, band 2 and band 1. A real time RGB image, okay, red, green, blue, RGB. It shows a smoke region, a smoky region has been shown. Clear information about smoke is there, and this smoke obstruct the ground view. The same image when you see in the panchromatic range, you can see that there is no information available, but when you only use a particular bands of information, for example here I have used RGB band, red, green and blue band, band 3 to band 2 and band 1, I get information that the image, the area is covered by smoke. Now this smoke can be due to some forest fire or due to some burning effect, or it could be some volcanic eruption also. Now I am using a different bands now. This image. Now here I have used band number 7, that is mid infrared, band number 5, that is again mid infrared, but the region is different, 2.8 to 2.5, and here 1.5 to 1.7 micrometer, and band number 4, that is near infrared, okay. Now this information shows me a different information. Now it shows me that there has been a smoke. The region has been covered by forest, a greenery. And now this amount of bulk in greenery is mainly due to forest. Using these 2 images, I can clearly say that there is a forest fire in this region. Now this type of information can be only available using the spectral responses by combining different type of spectral responses. Now you might be surprised with the color, but just for information, we have used a false color composition again. A false color composition, as I have explained earlier, in false color composition you use 3 particular images and you assign a color to them, okay. So using that we have done this. Now, another question if you have that how this area has been classified as green region. Okay, so for example, in the previous image, if you see RGB image, now this particular area has a particular this type of area, it clearly shows that it has been smoked. Now this one is one of the point. Now this one is also one of the. Now this and here there is also one of the. Now this type of information clearly shows that there is some burning effect going on. The darker the region makes it informative, shows the information that this particular area has trees or green effect, because in this particular image I have used black as a green for green band. The same area I have used here, and it could clearly show me that yes, of course there are some. This is much more clearer compared to a smoky image. But yes, from this I can clearly say that this point, and somewhere here, this point, there are some images of forest fire burning. So this type of spectral means in this way we can use the spectral bands information responses for detection of any particular event. Sometimes it is also used for the detection of mineral species also. For example, if you are talking about some planetary experiment, so if you have checked about this, you know about Mars orbiter mission, MOMS mission. So when you use MOMS output, it has also used some spectral resolution images like mid infrared and thermal infrared images, and some of the images from microwave region. So using those images, using those spectral band, information regarding the minerals that is available on a planet or on any particular on Earth also, on a particular region on mining site, you can clearly see, and you can say that this particular region has but there is a presence of this amount of particular mineral in there. So it is also not surety, the surety of it depends on the accuracy of your analysis and also on the accuracy of your sensor. But yes, you can use this type of analysis and this type of spectral bands for signature analysis and for their physical interpretation. So students, I hope you have enjoyed this lecture. Here I stop talking about the spectral resolution. In our next lecture, we will talk about radiometric resolution. So till then, happy learning. Goodbye.